This is the last video about dynamics, and we're going to be looking at air resistance here. In kinematics and in projectile motion, we said we're going to neglect air resistance for things that move through the air, but that's not very realistic except in a certain number of cases. So we're going to look briefly at air resistance. We'll do it qualitatively, and then we're also going to do it quantitatively. Now, the first thing to know about air resistance is that the faster you go, the more air resistance there is. Sometimes the air resistance goes as v squared. What that means is that the drag force is proportional to v squared. Sometimes it goes as v. Sometimes it's proportional to velocity, sometimes it's proportional to the square of the velocity. Which one it is something that you will be told at the beginning of a problem. So let's describe qualitatively the motion of an object falling with air resistance. So the first thing, draw a free body diagram. You've got the weight, mg, pointing downward, and then as it's moving downward, air resistance, Fd, is opposing the motion. And Fd gets larger as the velocity increases. So let's draw velocity as a function of time. So the first thing that's going to happen is the velocity starts out at 0. We know that. And initially, when the falling particle is moving very slowly, Fd is 0. So initially, v is 0, and so is the drag force. And that means the only force acting on this particle is gravity, and thus the initial acceleration is g. But as it speeds up, what happens is the drag force increases, which means that the net force on it decreases, because F net equals mg minus Fd. The result is that the acceleration also decreases. And eventually the acceleration reaches 0, and the velocity levels off at a value that we will call the terminal velocity. We can also plot acceleration versus time, and that's going to start out at g and gradually approach 0. And the last thing we can do is we can plot position versus time. And here we're taking downward to be positive. And so initially, the position versus time graph looks like a parabola, but it gradually approaches a straight line because the velocity becomes constant. So those are qualitative graphs of motion of an object falling with air resistance. Now, I've used this term terminal velocity. What that means is the velocity, or the speed it's moving at after a long time. Anyway, terminal velocity occurs when the drag force becomes equal to the object's weight. And calculating the terminal velocity is the easiest thing to do mathematically for a falling object. All you have to do is take the expression for d, which in this case is some constant c times v squared, set that equal to the weight, and solve for v. And there we go. So some things you can notice about this. If you want to have a high terminal velocity, you get something with a large mass but a small value of c, which means that if c is small, you want it to be aerodynamically shaped and relatively small in size. Now, for other objects, drag force is proportional to the speed, in which case the math gets even easier. Now we're going to do some probably the most difficult math you're going to see this semester. The first thing we'll do is we'll draw a free body diagram for whatever we have. So let's say a sphere falling through water, which, except we're going to change this. Okay, going back. A sphere falling through water experiences a downward force of mg, a resistive force that is given by F equals bv, where b is a constant. Notice it's not v squared. If it's v squared, it makes the math that much more difficult. What we want to do is find an expression for v as a function of time, and also find out how long it takes to reach 90% of its terminal velocity. So first thing, free body diagram. We have the weight force downward and the drag force upward. And so we'll write Newton's second law. The physics here is really easy. The acceleration is going to be downward. So ma equals mg minus bv. Divide both sides by m, we get a equals g minus b over m times v. There's our basic equation. You might remember the definition of acceleration here. Acceleration is the derivative of the velocity. And so we have an equation that has velocity on the right side and its derivative on the left side. This is something we call a differential equation. And they have this scary reputation, but the class of differential equations you'll have to solve for this class is pretty easy. It's basically this one. Most of the differential equations you see are variants on this. What we're going to do to solve this kind of differential equation is we're going to separate the variables. In other words, the two variables we're interested in are v and t. And we'll get all the v's on one side of the equation, all the t's on the other side. And then the constants, g, b, and m, we don't really care where they end up. So what we'll do is we'll say, okay, we'll divide both sides by v and multiply both sides by dt. So we get dv divided by g minus b over m times v equals dt. That's just algebra. And then what we do is we've got an integral on both sides. Now the left side, or the right side is easy. We'll do the left side first. It's a little bit more difficult. So we've got this integral, and we notice the form of it, and we're going to use a U-substitution. So we want to do this integral dv over g minus b over m times v. And we'll say, okay, our U-substitution is g minus b over m times v. du dv is equal to b, or negative b over m. And so here we've got 1 over u, and dv is just negative m over b times du. M and b are constants, so they can come out the front of the integral. And the integral of 1 over u is the natural log of u. That's easy. Which we can rewrite as negative m over b times the natural log of g minus b over m times v. That's the left side of the equation. That was the hard part. The rest of this is going to be easy. The other side, the integral dt, that's easy. T, and then we'll add the constant of integration to that side. We can choose which side we add it to, it doesn't really matter. And now the last thing we need to do, solve for v, because we're looking for v as a function of time. And we'll get rid of that. So we'll write down what we had there. So negative, gotta remind myself, m over b, natural log of g minus bv over m equals t plus c. And so the first thing we'll do is we will get multiplied by b over m. So we get natural log g minus bv over m equals negative bt over m plus c prime. See, that's just c times negative b over m. It's just an undetermined constant, so we can set it to be whatever we can rename it whenever we want. Next step, we need to get v out of that log, so we're going to take we're going to exponentiate both sides. Equals e to the negative bt over m plus c. And now we're going to, or c prime, and we're now going to make another constant, c double prime, which is equal to e to the c prime power. And so we get bv over m is equal to c double prime e to the negative bt over m plus g. And then v of t is equal to negative c triple prime which is m over b times c double prime e to the negative bt over m plus mg over b. And then what we do is we apply our initial conditions to find out what c triple prime is. And our initial condition is that at time 0, v is equal to 0. So we set 0 equal to negative c triple prime, e to the 0 is 1, plus mg over b, and that tells us that c triple prime is mg over b. And we will write our value, our expression for v of t is equal to mg over b times 1 minus e to the negative bt over m. If we graph that, it's a lot like what we got 2 slides ago when we qualitatively sketched the graph. For tomorrow, there aren't any questions in your homework that deal with this. So what I want you to do is find out, or finish this problem basically. Find out how much time it takes for v to reach 90% of the terminal velocity. So what you'll need to do there is find an expression for terminal velocity. Multiply that expression by 0.9, plug it into the equation, and solve for t.